Hi, everybody, and welcome to our third live lecture. So in this unit this week, we're covering three sections. So section 1.4, 1.5, and 1.6. And again, just as a reminder that my goal is to try to touch on each of the topics, but there are a lot more examples in your text. So three sections is a lot to try to cover in 1 hour. So make sure you're still reading your text for other examples as well. And, also check out my math lab if you need additional video resources. My lecture today will probably run a bit longer than usual, so maybe more like 70 or 75 minutes, just as a warning. So if you're watching the recording at home, then you can plan to watch the whole recording in one sitting, or if that's too much, you can break it up into different chunks. We're going to start with equations of lines. So an equation of a line can be written in different forms. So you can have it in point slope form, slope-intercept form, or standard form. So those are the three main forms we tend to see the most. And what you see with point slope form, I'm just going to kind of talk about these first two parts for a second, is that the form is y minus a number equals the slope times x minus a number. That's the general setup here. And you can see that in this first form. So you have y minus 6 equals, the slope here is 2, x minus 4. And specifically, x1 and y1 are some point on the line. Doesn't matter which one, any point is fine. The second form, which is the one people tend to be most familiar with, is slope-intercept. And you'll notice that you are solved for y here. So that is this one. So y is by itself. And in this form, your slope is right next to the x, and then the other value is the b or the y-intercept. And then the last form here we're going to talk about is standard form. And what you see here is that the variables are on the same side in this case. A, B, and C don't have to be integers, but typically they are. So a lot of times what we'll do if we're in standard form is we will clear out fractions and things like that, just to make it a little bit nicer to read. All three of these forms are great and have a purpose or a point. So the first form here, the point slope form, is most helpful when we're trying to write a line. And we know the slope and we have a point, but that point is not the y-intercept. It's something different. The second form tends to be a favorite because you can get a lot of information out of it. You have the slope and the y-intercepts very visible there, so it makes it easier to graph like we've seen. And you can also write this equation very quickly, again, if you have the slope and the y-intercept. Standard form tends to be nice a lot of times if we're modeling. So when I used to teach a different course, we would model sometimes larger real world problems. We'd have not just 2 variables, we'd have like 5, 6, 7, 8 variables. And in those cases, we do like to kind of keep them all on one side. It makes it easy to kind of say everything lined up and organized, or to use Excel files or other spreadsheet tools, right? If everything has a place, kind of a column, then it's nice and organized. So that form does come in a lot as well in other cases too. And the big thing is that they're all interchangeable. So in the example I have up here, these are actually all the same line, and you can go from one form to the other. So for instance, if I start with the point slope form here, I could distribute that to, I get 2x minus 8, and then I could add the 6 to the other side, and you'll see that we're now in the second form. So here is the first form, right? This is your point slope. And then now we simplify to be in the second form, which is our slope-intercept. So these are the same exact line. They just look a little bit different. We could also take it to the standard form. So if I'm just going to rewrite this over here so I have more room. In standard form, we like to bring everything to one side, meaning all the variables to one side. So I can bring that 2x over by subtraction. So I have negative 2x plus y equals negative 2. Now this is actually in standard form. A lot of people don't like the leading value to be negative. So what you see sometimes is people may multiply both sides by -1 or switch the sides. And you have 2x minus y equals 2. So this is actually the same answer as this one. It's just with the negatives reversed. So this is also correct. And again, this is standard form. Okay. I kind of equated to like if you change your clothes, right? So you're still the same person, but maybe when you go to work, you have to wear a uniform or a certain type of clothing. And then on the weekends, you wear something different. Or when you're going to bed, you wear pajamas, right? So you're changing your appearance, but the core of who you are hasn't changed. You're still the same person. And that's kind of what's going on here. The appearance of the line may look a little bit different in the different forms, but all the information is the same. If you were to graph each of these forms, you would see the same exact line each time. So we're going to start with how to write equations. So far you've been kind of given equations and asked to graph them or work with them, and now we're going to work backwards. We're going to write our own linear equations. And to write equations, you do need two things. You do need a slope and you need a point. If you have the y-intercept, it actually is nice and easy because you can use that slope-intercept form and just plug in the m and the b to find the equation. If you do not have the y-intercept, so if you have another point, then the one that I recommend is the point-slope form. And again, you plug in the slope and the point given instead. Now, alternatively, you could use the slope-intercept form and solve for b. So if you have another strategy that you've already learned on how to write equations that you want to use in this class, that's perfectly fine with me. I'm going to use these two strategies, but again, there are always others. So if you've learned one already, you're welcome to use it, and that is fine. We typically do write our final answer in slope-intercept form or standard form. Those tend to be the most common, but make sure you read. There are some questions where they may ask you to leave your answer as point-slope form, or they may ask you to simplify to slope-intercept or standard. So you want to read your questions really carefully in the section and make sure you're writing your final answer in the form that they're looking for. All right, so to kind of summarize here, when we write or find the equations of lines, we need two things. So you always need a slope, and you need some kind of point. Okay? If your point is the y-intercept, right, so you have the point 0, b, then I recommend that you use y equals mx plus b, because you can plug in the m and the b very quickly, and you're done. If you have any point though, and this also includes the y-intercept, so this method will always work no matter which point you have, I do recommend that you use the other form, so the point-slope form y minus y1 equals m times x minus x1. And that what we're going to do there is we'll plug in our slope and we'll plug in the values of the point, and then usually we'll do some simplifying and clean it up. So let's look at two examples here. So let's say a line has slope -7/9, and it has the y-intercept 0.16. So again, I need a slope, which I have, and I need a point, which I also have. Now, specifically, this is the y-intercept, right? So we know that the b value here is 16. So if I have the y-intercept, I'm going to use y equals mx plus b. That is the easiest way to do it. And then all you need to do is replace the m and the b with what the problem gives you. So -7/9 x plus 16. And that's it. Now, if this was a -16, you could do plus -16 or -16. That would be fine as well. For our other example, this one's much more complicated. So we are given 2 points here. Notice how neither is the y-intercept, right? It has to have a 0 in the x spot to be the y-intercept. These do not. So they're just other points on the graph. I still need a slope here, and it's not given to me, but you should have enough information to find it. And if I think back to a previous lesson, I had a formula, y2 minus y1 over x2 minus x1, that let me find the slope between 2 points. So again, when you're writing equations, you should have enough information, but you may have a little bit of work to do. So I'm going to start and do -4 minus 3, -1 minus 2. So I have -7 over -3. I do want to simplify my fraction here. Let's see. Did I make a mistake? Oh, I did. Hang on. That looks better. This is a +1 minus 2. Oh, this is much easier. -1. There we go. And I do have positive 7 here. If I did have a fraction, then you can just work with a fraction. It's not the end of the world. Maybe just a little bit more work there. So here again, just be careful. I make mistakes too. That 1 was positive, not negative. I copied it wrong. 1 minus 2 is negative 1. So my slope is just positive 7. And I'll tell you guys too, I always do my lecture notes out before I come to class with you guys. So I have what the answers should be ahead of time. So if I always check as I'm going through to make sure I don't make any silly mistakes. Or if I do, I correct them right away. So that's why I'm able to catch them, because I've already done these problems a few times before the lecture. Now for the point, you can choose either one. It doesn't matter. You'll get the same equation in the end. So I tend to like to use 2, 3 because it's all positives. It makes it a little bit easier, but you could use 1, negative 4 also. So this is the x value, right? So that is like the x1. This is the y value, right? This is not the y-intercept. So I'm going to use the other form. Y minus y1 equals m times x minus x1. And I'm going to replace the y1, the m, and the x1 with the values that I have. So my m was 7, for instance. My y1 is 3, and then that 2 is going to go in for the x. So it'll be y minus 3 equals 7, x minus 2. And just be careful, you know, if you have negatives, watch out. If you have like a double negative here, you could change it to a plus sign. So you do want to just watch out for those little details. This right here is the point slope form. I am going to clean it up though, which is pretty common. So I'm going to go ahead and keep multiplying this out. 7x minus 14. Then I'm going to go ahead and add 3 to both sides. And I get y equals 7x minus 11. So this would be the slope-intercept form, which is the most, I would say, probably the most common form that we end up writing our final answer in. Now, I'll let you try this at home. I'm not going to do it out, but if you try 1, negative 4, and you plug in, your initial point slope form will look different. You'll end up having y plus 4 equals 7 times x minus 1 instead. But when you multiply everything out and simplify it, the slope-intercept form will be the same. So it is the same line. Again, it may look a little bit different to start because you're using a different point, but if you do clean that up, you will see the same answer in the end. So give that one a try at home and make sure you're getting the correct result. All right, so next I want to look at two lines together. And lines can be parallel, perpendicular, or neither of these two. So let's look at the 3 cases. All right, so parallel lines basically look like this. Or this is one example, I should say. So things to note is that they do not touch. And also they have the same slope, which is why they don't touch. They also would have different y-intercepts. So like they are different lines. They're not the same line written twice or anything like that. They are different lines. They do have the same slope, but they don't touch. They would forever, never, ever meet. Because they have the same slope or slant, they will never cross. Perpendicular lines look like this. So they intersect at a perfect 90-degree angle. And what happens is their slopes are what we call negative reciprocals. So what does negative reciprocals mean? One, they have different signs, meaning one's positive, one's negative. And then 2, they are flipped versions of each other. So for instance, one could be 3/4 and the other slope is negative 4/3. So different signs and flipped versions. So also called reciprocals, right? They're reciprocals of each other. The other thing to note too is, and I have a little mistake down here I want you guys to fix, is you can always check perpendicular lines, because their slopes produce a product of -1, not +1. So if you multiply these together, for instance, 3/4 times -4/3, you have -12/12, which is -1. So you do always see that with perpendicular lines. And then the last case is neither. Basically, we just don't give any other special names to other intersections. So they definitely cross, but not in a special way. So meaning that either, the slopes are not the same or they're not perfect opposites. They do cross, they have different slopes, but again, I don't really have a special name for them. Vertical lines are also parallel to each other. Vertical lines, remember, have slope that's undefined, so they are still parallel, but to each other. And then non-vertical lines, like I said, are parallel if they have the same slope and different y-intercepts. So for instance, here's one line. Notice how this line is already in the y equals mx plus b form. Because of that, I can pick out that my slope must be 2 and my b value must be 7. Now, this line here is not in that form. So if you have a line that's not in the right form, you're going to have to solve for y to find the slope. Don't just try to guess it. So I can add 4x to both sides, try to get that y by itself, divide by 2, and then just don't forget you're dividing everything by 2. So 4 divided by 2 is 2, and then 8 divided by 2 is 4. So here, your slope is 2, and then your b is 4. So again, they're different lines because their b values are different. They're not the same, but they do have the same slope. So same slope. This is 2. So they are parallel. As I mentioned, lines are perpendicular if their slopes are negative reciprocal, so they produce a product of -1, product meaning to multiply, right? They multiply to -1. Here's just another example, -3/8 and +8/3, right? So you see one's positive, one's negative, and then you have that flipping, that reciprocal idea as well. And again, if you multiply them together, you can see that the numbers cancel across, so you are going to get that 1. But if you forget, you can always just multiply across. This is a 3, and I still get -1. As another example here, let's say your first slope is 4, your other slope is -1/4. Remember that with whole numbers, you can always put them over 1. So if you're looking at perpendicular, when you flip that, that 1 is going to be in the numerator. So this is how you can see a perpendicular example with a whole number. So 4/1 and -1/4, for instance. And then vertical and horizontal lines are perpendicular to each other. They do intersect perfectly at 90-degree angles. And that's a great example to just look around your room that you're in. You probably see lots of vertical and horizontal lines that intersect perfectly at 90 degrees. All right, so to answer this question, determine whether each of the following pairs of lines is parallel, perpendicular, or neither. What you really want to do is to compare the slopes. And that probably means getting them in the y equals mx plus b form. So you don't want to just graph these lines. Graphing them can give you an idea, right? It may kind of point you in a direction like, hey, these look like they're vertical, or sorry, these look like they're parallel, or these look like they're perpendicular, or these don't look like they're either. But it's not perfect. So for instance, right, if I'm graphing something and one of my equations has slope 5 and the other one has slope 5.1, I probably am not going to be able to tell the difference between that visually, just with the human eye, right? It's going to be really hard to see that those are actually different. They're probably going to look the same. So you really need to actually do out the algebra and compare the slopes, not just rely on graphs here. All right, so for these cases here, I don't have anything totally solved for y, so I do need to get the y by itself. On my first example, I have y plus 2, so I want to get that 2 to the other side. I'm going to subtract it, and I get 5x minus 2. So now I'm in the right form. Remember, your slope is always with the x. So our slope here is 5. And again, our y-intercept is -2. Here, I want the y by itself. I got to start by bringing the x over. So you want to try to get everything away from the y first by adding or subtracting. And then if there's something attached, then you can go ahead and divide by it. So I have y equals. Now here, be careful, there is a 1 in front of the x. So it's negative 1/5 x minus, and then 15 divided by 5 is 3. Remember that division goes in both directions here because the whole thing is over the 5. So my slope here is negative 1/5. Now if I compare these two, I have 5 and I have negative 1/5. I do see that these are negative reciprocals. Right? I have both a flipping, right? 5 over 1 becomes 1 over 5. And then I have the sign change. So if I have this happening, then I have perpendicular lines. And this is a good time to check with the graph, right? So you know that the perpendicular, you could check with the graph now and make sure you get that right picture. And if you don't, then maybe something's wrong in your algebra. So the graph is a good way to kind of check or point you in a direction, but the algebra is really where we want to confirm about the slopes. For the second case here, again, I need to get y by itself. So I always start by adding and subtracting first. So I have 2y equals negative 4x plus 8. Then I'm going to divide everything by 2. Now, negative 4 divided by 2 is negative 2, and then 8 divided by 2 is 4. So in this first example, I'm getting a slope of negative 2 there. Now in the second example, I actually have y almost solved by itself, right? It just had this negative here, so I could divide everything by negative 1, and I get negative 5 minus 2x equals y. So all those signs switch over. Now this is actually fine, but you may find this kind of weird looking. So what you could do is just rearrange it so it looks more like what we're used to. So instead of having the y on the right side, I probably want it on the left side. I'm not going to solve, I'm just going to flip my two sides, which is perfectly fine to do as long as you don't change anything, right? So the y is still y, 5 minus 2x is still there. So you can reverse their sides because they are equal. And then I can also flip these. You just have to be careful that you don't mess up the signs. So it's a negative 2x and a minus 5. Again, subtraction is not commutative. So again, you're kind of thinking this as like a plus negative 2x. So as long as you flip it around and you don't mess up the signs, it's okay. So this is the form that you're probably most used to. And now I can clearly see that my slope here is negative 2. So I have the same slope. And I do have different y-intercepts, right? One is 4, one is negative 5. So they actually are different lines. It's not the same line written twice. So these are actually parallel. And then for my last example, the y here is already by itself. Again, if you don't like it on the right side, you can reverse the sides as long as you don't change anything. And then now I can see that my slope is right here. It is the 2. Here, I do have to bring the 3x to the other side. Y equals negative 3x plus 4. Now y is by itself, and I can see my slope there is negative 3. Now, these slopes have nothing in common, right? They're not the same. I know I have a sign change here, but they're not reciprocals, right? They're not flipped versions of each other. So this is an example of a neither. So they just don't have much in common, right? Couple other neither examples, just to kind of watch out. Let's say your first slope is 2 and your second slope is 1/2. This one always throws everybody off because you have the flipping action, but you don't have the sign change. So it's still a neither. Or maybe you have the 2 and then it becomes a negative 2. So again, you have the sign change here, but not the flipping. So these pairs, like this is one pair, this is another pair, these are still neithers. So even if you have one change, it doesn't matter. You need both changes for something to be perpendicular. All right, so the next thing I want to touch on here is curve fitting. So curve fitting is when we can find a function that fits our data well. This is something we do a lot in statistics particularly, so they're just doing like a quick little introduction here to this. So typically what you do when you have real data is you would graph it first by creating a scatter plot. So you would have XY data and you would just plot all the points on the graph. And you wouldn't connect them with a line or anything. You just plot just the points, and you'd have a bunch of them, probably like 100 or 200 or something like that. And then you look at it to see if there's a pattern. Sometimes when we plot things like that, you may see a pattern. Other times you may not. So if you see a shape, like let's say it's like, hey, this looks like it's a line, then a linear function may be a good fit. Or if you see a certain curve, maybe a function that's a curve would be a good fit, and so on. So a lot of this is done with technology too, because it's actually quite difficult to do by hand. But it's just kind of an introduction to the idea that functions do have a purpose for real world data too. If we find patterns there, then we do try to find functions that fit that data. And again, we usually use technology to help us because it's usually quite difficult with a lot of data points. I'm going to share with you guys this first one. Oh, so my hair's sticking up on Zoom. All right, let's see. All right, I think this is the right one. Let's see if this works. Perfect. Okay, so this is that first link there, and it just kind of gives you this introduction to scatter plots. So a scatter plot looks like this. It's just the points of the data. We're not connecting them or anything like that. We're just kind of graphing all these points. And then what you do is you look to see if it kind of looks like it has a shape. So here's an example of ice cream sales versus temperature. And it is in Celsius, so it may be a little bit harder to read, but you can kind of see, hopefully we're here to see a pattern, right? My guess, my hypothesis would be that as the temperature gets warmer, ice cream sales would increase, right? Although I won't lie, I did go and pick up ice cream last night, and it was about 25 degrees where I live, but it was still really good. But we definitely don't do that as much in the winter, right? We tend to go for ice cream usually more in the summer when it's warm out. So what we would do is we take this data and we're going to plot it on a graph. And they did that already for you here. So they have temperature as the x-axis and sales as the y-axis. And you can see that the graph looks pretty linear. It kind of looks like a line. Now, I will tell you that with real world data, it is extremely rare that it would ever be exact on a line. I'm sure there's a few exceptions out there that I'm not thinking of, like maybe in manufacturing or something like that, where things are pretty consistent. But in general, with real world data, it's messy, it's not perfect. So we look for the best fit that works. So if I look at this data, it does look pretty linear. Even though it's not perfect, I do kind of see that increasing line there. So I would say that a linear function would be my best fit. So I would try to see if I could get technology to find an equation for me that mirrors this data. And that line is called the line of best fit. Or if you have other things like a curve is fine, that we can do other ones as well. This one has a line, so we would use technology to help us find that linear equation that best fits the data. We can do it by hand. It's a little bit less exact, but you could do it, for instance, taking like the first point and the last point and using that to find slope in an equation of a line. So sometimes we'll do that by hand just to kind of try it out, but the technology will give you a better result. But that's really sort of how it works. And here's another example of, this one's also linear, of sea level rise. You can see the graph looks pretty linear there. And then technology was able to find a line of best fit. Again, the points are not all going to lie on it, but hopefully it's a pretty accurate line to give a good estimate, right? And that's really what we're looking for. And then we're able to use that line to help us estimate, looking for other data points, within the data and getting an estimation there. Or, you can go a little bit outside the data as well. That's called extrapolation. You just don't want to go too far outside, right? So maybe I would go to 26 degrees or maybe 28, but I probably wouldn't want to go too far beyond my data set. You got to be really careful there because things change very quickly. So here's an example of trying to estimate like outside the data set. Okay. All right. So let's go back to our handout and we'll kind of keep going. So that was the first part, is really looking at slope, a little bit more of the different types of lines, parallel, perpendicular, neither. And now we're going to kind of almost like backtrack a little bit, go back to just one variable and just do a quick review of how to solve linear equations, particularly ones that are a little bit more complicated. So a linear equation in one variable, again, we're kind of backtracking a little bit here, is an equation that can be expressed in the form mx plus b equals 1. Now, a lot of times they look a little bit more complicated than that, but you could simplify down to that form. The big thing with linear, remember, is that for right now with linear, you're not going to have any squares or cubes or higher power exponents, and we're not going to be dividing by variables, so they're going to be, relatively straightforward. I do have a typo here. That should be same. Equations that have the same solution set are called equivalent equations, and that word equivalent basically means equal, right? So when we're solving, we basically go through a process that gets us to the answer by going from one equivalent equation to another. So when we make changes and we start solving, we've been doing a little bit of this already, we don't change the solution. So I may change the look of what I'm doing, but I'm not messing up the solution, and that's the key here. That's why we have all these rules. So ones that we've already been using, the addition principle. So if you add the same number to both sides or subtract it, then again, it's still going to be the same solution. The same thing is true for the multiplication principle. If you multiply by the same number on both sides, or if you divide by the same number on both sides, as long as it's not 0, then again, you get the same solution. So it's basically okay to add or subtract or multiply and divide. As long as we do it equally on each side of the equation, our solution will not change. Now, as you get through more complicated examples that are not just like 1 or 2 steps like we've seen so far, how do you start them? And there's different ways to do this, of course. The way that I like to do it is I tend to always do my parentheses first. I think that's the easiest thing to do. And then if I have fractions or decimals, I can clear those out by multiplying. So I'll show you a fraction example in a minute. And then I also like to combine like terms on each side of the equation. So I don't move things around yet. The first big step, and this is the hardest, is just kind of clean it up as much as you can, right? Combine things that should be together, get rid of parentheses and that sort of stuff. Once I've cleaned it up as much as I can, then I start collecting. So now I start adding and subtracting the same number on both sides or the same variable on both sides. Once all my like terms are together, then I'm going to divide. And I'm going to divide by whatever number is with the variable. And then finally, you can check. So you can always check your solutions by plugging them into the original equation to make sure you get a true statement. So here's our example. I see lots of parentheses, so I'm going to start by clearing those out first. So I'm going to distribute the 2. I get 10 minus 6x equals. Now on the right side, you want to be a little careful. You have a minus 3 here. So when you distribute, you actually are distributing that negative 3. So it's 8, and then minus 3x, and then negative 3 times 2 is negative or minus 6. So watch out for that minus sign there. Now what I do, I don't have any fractions or decimals, but I'm going to look at each side of the equation first. So when I say sides, like here's my equation sign, right? I'm going to look at the left side and the right side and see if there's anything I can do that's easy. While on the right side, I do see an 8 and a minus 6 that should go together. And 8 minus 6 is 2. So I'm going to get 2, and then I bring everything else down. Now, there's nothing on the left side I can do. These are different kinds of terms, so I can't combine them. And at this point, everything is cleaned up, so I'm ready to move on. Now I'm going to start rearranging. So I want to get my terms together that are the same, and I'm going to have to cross over the equal sign. It doesn't matter if you bring your x's to the left or to the right. I think most students like them on the left, so I'll do that, but it doesn't matter. So I want to get this 3x over here at the 6x. Well, when we're changing sides, we're going to change the sign. So if it's a minus 3x, it's going to be a plus 3x when I move it to the other side. And the reason that works is because minus 3 and positive 3 are 0. So it will cancel it from the right side and bring it to the left. Negative 6 plus 3 is negative 3. Now I want to bring the 10 over with the 2. It's a positive 10 here. So when I bring it over, I'm going to use a minus or negative 10 because 10 minus 10 is 0. So that will cancel it. And let's see, 2 minus 10 is negative 8. Now, notice all my like terms are done, right? My x's are here, my numbers are here. So the final real step is to divide, and you always divide by whatever is with the x. So you use the same sign, whatever is there, that's what you divide by. And then you can go ahead and clean it up. So negative 8 over negative 3 becomes positive 8 over 3. If I could simplify this, I would, but that's usually fine. Usually for us, it's fine to leave it as an improper fraction. You can check in my math lab to see how they want your final answer, if they want something different, right? If they want a decimal approximation or if they want a mixed number or something, but as long as it's simplified, it's usually okay. I'm not going to do the check here because our video is going to be long enough as it is, but if you wanted to check, you would take your answer and you would plug it in into the original equation. And that's actually really important that you go right back to the beginning. So I would take my original equation and I would replace any x with 8/3 and then I would keep simplifying and see if it actually works. So if the two sides are the same. Now you can also use your calculator to check as well. You may get some decimal approximations there, so you could be slightly off because of a decimal issue, but they should be extremely close if you're using your calculator to check. If you don't want to deal with some of the fraction work here, but it's really not too bad because a lot of those 3's are canceling out. So give that a try at home, and again, you should get a true statement so that you know it is correct. If you're doing a check and you get a statement that is false, I would check your check first before you erase all of your work. So a lot of times students are rushing through the checks and they may make silly mistakes. So I do always recommend if you get something that doesn't work out, make sure you didn't make a mistake over here before you start erasing your whole problem. And if you're still seeing that it's not working out, then maybe go back and solve again. Or you can always reach out to me as well if you can't figure out where your mistake is. All right, so here's an example with a fraction. And I definitely want to do one of these. So what we can do is we can clear fractions by multiplying everything by a common denominator. So I would still do parentheses first. That's my personal choice. You can clear fractions first if you're comfortable with it, but I do find those parentheses kind of get in the way sometimes. So I do like to clear out parentheses first, and then if I have fractions, I deal with that second. Now, you don't have to use this strategy. If you don't mind working with fractions, then you can just solve as usual. Just be careful about working with fractions. Most students don't like fractions, so I find that clearing them really helps. So notice here that I have two denominators. I have a 4 and a 5. So what you want to do is find a common denominator. You can find the smallest one, the LCD. That's the best because it'll make your number smaller, but just any common denominator is fine. So 20 works here because both 5 and 4 go into 20. So what I do is I multiply both sides by 20. And remember, it's fine to do this because I'm multiplying both sides equally. So what you end up doing is you do distribute through, and you'll see that basically when you use this strategy, you end up multiplying every part by 20, including the 1. So even though there's no fraction here, I still have to be consistent and multiply through. Now, the next thing you want to do is you want to do your division. So notice how you have a 20 over 4. 20 over 4 is 5. And then over here, 20 over 5 is 4. If you've done this correctly, your denominator should cancel out perfectly. And then you multiply what's left. 5 times 3 is 15x. Here, 20 times 1 is 20. And then 4 times 7 is 28. And now I have a much simpler problem to solve. So it's more work up front, but it ends up probably being quicker in the long run because you deal with the fractions right away and then you don't have to keep dealing with them over and over again throughout the problem. Now I can just solve. I'm going to add 20 to both sides here. I'm going to divide by 15. And I have x equals 48 over 15. And then we can definitely simplify this. These are both divisible by 3. So I have 16, over 5 there. Sorry about that. 16 over 5. Again, if you want to use a mixed number, 5 goes into 16 3 times with a remainder of 1. So it would be 3 1/5. But usually, I'll just write that again for you guys. 16 over 5 would be fine unless it is requesting a different form. Now, usually we get one answer for linear equations, but there are some exceptions where we can get infinitely many solutions or no solution. So here we're going to solve these two, and you're going to see these two are going to come out a little bit different. So in this case, the first one, I don't have any parentheses, I don't have any fractions, decimals, nothing like that. So what I can do is just start combining like terms. There's nothing to really do on either side. So I would like to get my x's together and bring them on the left. Negative becomes positive. And what you're going to see happen is that it actually cancels on both sides, right? Because negative 24 plus 24 is 0. This is not x. This is 0 times x, which is 0. So this is gone. And I have 7 equals 17 left. So this is false, right? 7 is not 17. So something like this would be a no solution. Notice that in this case, what happens is the variables cancel out, like totally cancel out, right? They're gone. So that's what you're looking for in a linear problem that is an exception problem. For this one here, it's a little hard to see, but this is the number negative 1/3 in both cases. So I don't have parentheses and things, but I do have fractions. So I would like to clear up my fractions to start. And if my two denominators are 3, I can just use 3 for my LCD. So I'm going to multiply 3 on both sides, which means I'm going to distribute through to each part. So I have 3 times 3 minus 3 times negative 1/3, positive 1/3 x. So I just have to be careful there. I have a positive 3 and a negative, so it's just going to be one negative sign or minus sign. Here, again, I have that 3 I'm distributing through. And now I'm going to go ahead and start canceling. So here, 3 over 3 is just 1. And then I multiply what's left in those cases. So 3 times 3 is 9. 1 times 1 is 1, so this is just 1x or x. Again, 1 times 1 is 1. Be careful, you do have a negative there, so it's going to be negative x. And then 3 times 3 is 9. Now, again, it looks a little bit weird, so maybe you're probably guessing that something's going to happen. When I try to get my x's together, again, they cancel on both sides, and I'm left with 9 equals 9. Now, this case is true, so we actually have infinitely many solutions. Many solutions. Other ways to say this, we call these types of equations identities. So we say it's an identity. You can also say that all real numbers are solutions. You can say that everything is a solution. Okay, so they all mean the same thing. So basically anything works. So you can plug in any single number and you will get a true statement. On the homework, quizzes and things, watch out for these. You shouldn't see that every single problem is going to be an identity or no solution, though. I'm sure you'll see some, but if you're constantly getting no solutions or identities, maybe slow down, double check your work, or come see me, or virtually see me, or get some tutoring there. There's something to watch out for, but it shouldn't be every single problem. In the real world, we definitely have no solutions. There's definitely examples where, maybe we're trying to create a new product and it's not linear, but the cost of the product is more than what we're going to make. So that's like a no solution. At that point, that product is done. We need to go back to the drawing board and see if we can maybe reduce our costs and start over. But sometimes you do have that there's no solution to an initial problem until we can go back and tweak it. Identities, I have never found an example in the real world that exists. Again, I don't want to say there's not one because maybe I'm missing something, but it would be really strange to have a real world problem where everything is a solution. So these are more algebraic based. All right, so now that we've finished our review of how to solve equations, I'm going to do some examples on applications. And these take some time. So if you're pausing at home, this could be a good time to pause and take a break because we're at 50 minutes, and then we'll do some application problems now and a little bit with linear inequalities. All right, I'm not taking a break. So if you're in for it, let's keep going. Really need to go back and read that text to see other examples as well. Now, word problems are always tricky. So I'm going to try to show you some strategies here to help you, but every word problem is different. So it's not as prescriptive as solving an equation where you know the steps are always going to be kind of the same. It really depends on the key words and what you're trying to find. So hopefully between these examples and the ones in the text, you'll have enough knowledge to be able to answer the homework questions, right, and apply what you learned in new scenarios. But you'll see a lot of similarities between wording and keywords and things like that. All right, example 9. Companies in China purchased 36,560 industrial robots in 2013. This is 54% more. This is 54% more than the number of industrial robots purchased by companies in the US. How many industrial robots were bought by companies in the US? So the way I like to start, and I do actually like to write this out, is I like to write out the goal and what I'm trying to actually find. So that's usually your question. And our question here is, how many robots were bought by the US? Right, in 2013. And again, I don't have to write it in full sentences. I just need some like key points here. So I'm trying to figure out how many robots the US purchased. Now, the nice thing about the goal is that it will help you figure out your variable. There we go. So the goal will help us figure out our variable. So we're only looking for one thing, right? How many the US bought. So this is going to be our variable. The number of robots purchased by the US is going to be X. Now, if you want to call it R for robots, go ahead. It doesn't matter which variable you use. I like to write this out to help clarify what we're letting X be. It is helpful as you go through the problem to stay organized, but also when you go back and you're trying to study for a quiz or remember what you did, you have those little key features that remind you, oh yeah, that's what X meant here. So again, I recommend writing these things out. Now you need to look at your information and try to create an equation. So I know that China purchased 36,560. I know that this is 54%, so this number here is 54% more than whatever the US purchased. So China purchased more than the US is what they're telling us here. So kind of breaking this down, the number that China purchased is the number that the US purchased, but plus 54%, right? Because it's 54% more than. More than means to add. So whatever the US purchased plus 54% is what China had purchased. And again, I like to write words first. Now, how many did China purchase? We know that was 36,560. How many did the US purchase? I don't know, but I've called it X. So I'm going to use X. Now, the only thing here is with percents, we typically like to use them in the decimal form when we're using like we're multiplying and things like that. So I'm going to take my decimal point and move it 2 spots left. So it's going to be 0.54 instead. And when we have percents, they very rarely stand by themselves. Again, there's always exceptions, but a percent of something is always percent of something. So you're multiplying this. So it's 54% on top of whatever the US purchased. So it's going to be 0.54 x. Now I can go ahead and solve this. Here I'd have a 1, so this becomes 1.54x, combining these together. I can divide both sides by 1.54, and I have that x is about 23,740.2597. So the US bought about 23,740 robots. It's always good to get in the habit of answering a question that's a word problem in a sentence, or at least a quick sentence. If you forget what you were trying to answer, you have your goal and you have your variable. So you can remind yourself, okay, what was X? X was the robots purchased by the US. Now I am rounding here. You're probably saying, well, why did you get a decimal if it's the number of robots? You can't have a fraction of a decimal. And my guess is that the rounding error is probably in the 54%. So 23,740 is probably the exact number. And then when they divided with that to get the percentage, they got a decimal answers and they only gave you the whole number. So there's probably a little bit of rounding error there in the percent form. There's no perfect check, but you do want to make sure it makes sense. Remember we said that China had purchased more than the US. So that looks good, right? China was at 36,000, the US is at 23,000. So we're going in the right direction there. And again, I think I've used all my information correctly. So it's not a perfect check, but you do want to make sure that your answer at least seems reasonable at the end. All right, here's another example. In the 2012-2013 school year, 47,058 US students studied abroad in Italy and in France. So this number here is the total for both Italy and in France. There were 12,638 more students studying in Italy than in France. Find the number of US students studying abroad in Italy and France. So what is our goal? To find the number of students in Italy, and to also find the number of students in France, right? We actually have two things we have to find here. Now, when there's two things we're finding, I don't want to use two variables. I know that's our nature to say, oh, we'll use two variables here. But when you have two variables, you would actually need two equations, and you'd have to solve systems of equations. Or if you have three variables, you need three equations, and you're solving systems of equations, which is a lot harder. So we want to try to get this to be just one variable. So usually, if you read through carefully, at least in a lot of cases, one part will have more information than the other. So for instance, here, we see that there were 12,638 more students in Italy compared to France, right? So Italy has more. So for the number of students in Italy, this is basically 12,638 more than France. Now, I don't know what France is, right? But I can use an X for France or an F for France if you want. And more than means to add. So I can write this instead as 12,638 plus X. And then I can let France be the variable. So again, sometimes you may have one part that has additional information, which lets you not have to use a second variable. So here, because Italy is being compared to France, I can let France be the variable and write everything else in terms of that X. The other information I have here is just the total. So the number of students in Italy plus the number of students in France is going to be that total 47,058. How many students are in Italy? Now I don't know, but I know how I wrote my expression. It was 12,638 plus X, and then the number of students in France was just X. You don't really need parentheses here. I just wanted to show you the two parts and how they're being combined. And now you're just doing algebra. X plus X is 2X. We're going to subtract that 12,000 value from both sides. and we're going to divide by 2. And if you do all this out, you should get that x is equal to 17,210. Now, we still have to answer the question, right? How many students are studying in Italy and France? So, well, I know my x value. My x value was France, right? So the number of students in France is 17,210. Now, how do you get the number of students in Italy? Well, go back to your startup here. Italy was x plus 12,638. So I can take my x value and add it with the 12,000 and get my answer. And you should get there 29,848. Now, again, I don't have a perfect check, but there's things that you can do. So one, we said that Italy did have more students. So you should see that the value for Italy is greater, which it is. The other thing that you could do here to check, and I'll let you try this at home, is you could add up that 29,000 answer and the 17,000 answer and make sure it does give you the total of 47,058, right? That's another nice way that you can check to make sure it's on track. And it's not a perfect check, but again, it gets you in that right direction to make sure that you don't have anything obvious going on, right? For instance, if I got like a negative answer here, that would definitely not make sense, right? I can't have negative students. Some examples you could have negatives, but not in this case. Or if my Italy number was too low, for instance, right? If it was smaller than France, I would know something is wrong. So you want to give it a quick kind of overall check at the end and see if it looks like it's going in the right direction. So this is a great example of two unknowns where you have additional information to help you write one of them as an expression instead. In the next example, we're going to have two unknowns, and this one's going to be a little bit different. So here, Demarian has two student loans that total $28,000. One loan is 5% simple interest, and the other is 3% simple interest. After 1 year, Demarian owes $1,040 in interest. And I want to know, here's my question, what is the amount of each loan? Now, this example is using something called simple interest. And simple interest is exactly what it said. It is simple. So what simple interest does, I is for interest, is it takes the principal, which is the, you can call this the amount of the loan, or if you have a savings account, it's the amount in your savings account, multiplied by the rate, which is the percent in decimal form, and then multiplied by time. Now in this case, our time is 1 year. So if we're multiplying by 1, we don't really need that piece here. So for this example, we're just using P times R, the loan amount times the rate. This is not really how it's done, if I'm being honest. Most loans use compound interest. So to figure out like monthly payments and things like that, it's a bit more complicated, and you end up usually paying more interest in the long run. So this is a very simplified answer. And in the real world, it would be a bit more complicated than this. But it's still a nice introduction to the idea of interest rates, and then also this type of problem where we have two unknowns. But if you read through again, I don't really have information about one loan compared to the other like I did with the Italy and France idea. I kind of have two unknowns, and there's really nothing for me to go on there. I'm just going to see if I can brighten this a little bit. There we go. So I need to find the amount in loan 1. I'm going to call that the 5% amount, or the loan, and I need the amount in loan 2, which is the 3%. Again, I don't have any extra information here that says that, you know, one is this much more than the other, or one is, you know, twice the other. There's nothing like that. They're kind of equals here. So I need to find a way to express them. And the way that you can do that, and this is a common way to kind of start with a problem like this, is to let one of them be x and let the other one be a total minus x. For instance, I do know that the total amount of the two of them is 28,000. So if I know the first loan, let's say, is 18,000, then the second loan must be 10,000, right? Because I need the total to be 28,000 altogether. So this is a way that we can write when we have two unknowns, and I don't have anything that I really know about them except for the total here. So this is a little trick that you can use for this style problem. The other thing that we know is we only know the interest amount. So basically the interest from loan 1 plus the interest from loan 2 has to equal the total interest. Now, interest is typically the fee that you would pay the bank for taking out loans. Or if you have a savings account, it's the fee that the bank pays you for letting them use your money and keep it in their accounts. So interest is found again here by just taking the principal and multiplying it by the rate. The principal is the amount of the loan. So for loan 1, the loan amount is X. I don't know what it is. It's just X. That would be the P. And then the rate here is 5%, but again, we don't use just the 5%. You're going to use the decimal form. So I'm going to go 2 spots to the left. So it's going to be 0.05. For the second one, the loan amount is this value right here, 28,000 minus X. And again, my rate is 3%. So I'm going to use 0.03. And then the total interest is 1040. Now I'm going to go ahead and solve. So this is just 0.05x. That 3 has to get distributed, or that 300ths has to get distributed. And you get 840 minus 0.03x. If I can combine my like terms here, I get 0.02x. Then I'm going to go ahead and subtract that 840 from both sides. And I get 200. And then finally I divide by 0.02, and I have X is equal to 10,000. So what does this mean? Well, remember X represented the first loan. So this means that, loan 1 is for $10,000, right? Because that was the X here. And loan 2 was the 28,000 minus whatever X is. So in this case, loan 2 was the 18,000. So we're able to kind of backtrack and find the original two loan amounts. This one is definitely more challenging because it brings in not just some tougher algebra, but also some new vocab. If you're not familiar with interest, it could be very different. But this is one to keep in mind. You do see a lot of these in the texts. They do come up on homework and stuff. And this trick here of letting one be X and one being a total minus X is a really nice strategy to keep in your back pocket if you can't figure out another way to start. So you can see if that works. My last example here for our applications is a geometry one, which I really like. So again, I tried to bring in a couple of different style ones. So we know the length of a rectangular solar panel. So rectangular solar panel, right? We'll call this the length, call this the width, is 13.6 inches less than twice the width, and the perimeter is 207.4 inches. Find the length and the width. So there's our goal. So I have two unknowns here again. I have the length and I have the width. I don't want to let them both be variables because I'm not going to be able to really solve that. So I need to figure out how to write it. And here I do see that the length is 13.6 inches less than twice the width. So I can fill that in. 13.6 inches less than twice the width. So the only thing is, how do you express this? This is a tricky one. This word than, also the word from, in case you ever see like subtracted from, for instance, reverse the order. So we actually start with twice the width first. So let's call width X. So twice the width, twice means to times by 2. So this is going to be 2x. Less means minus, and then 13.6. So for subtraction problems, be really careful of the word than and also the word from. They're going to switch that order on you, and it can affect your answer. So this should be written 2x minus 13.6. Now the other thing is that you have the perimeter. So perimeter, you can do it a few different ways. If you have a rectangle, the formula for perimeter is twice the length plus twice the width. But it also just means to add up all sides. So if you forget the formula, any shape, it doesn't matter for perimeter, if it has sides, you just add them all up, and that will always give you the perimeter as well. So filling in here, my length we called 2x minus 13.6, and my width we called x. You do want to be careful. Most students forget that there's 2 lengths and 2 widths, so that's why you have this multiplier by 2 there. And then we're going to go ahead and solve. So I have 4x minus 27.2 plus 2x equals 207.4. Combining like terms, I have 6x minus 27.2 equals 207.4. I'm going to add that 27.2 to both sides, and I get 6x is equal to 234.6. And I divide by 6 on both sides. And I'm just using a calculator for all of this work here. So I have my answer that x is 39.1. And again, don't forget to go back and remember to actually write a sentence here, right? They don't want to know what x is. They want to know the length and the width. So x was our width here. So our width is 39.1. And this was all in inches. So inches. And then our length was twice the width minus 13.6. So if I do this part out here, then I get 64.6 inches as that value. So there are my 2 parts. Now, how can we check this? Well, one, make sure it's going in the right direction, right? Does this make sense? So yes, the length is twice the width minus 13.6. So okay, I did my math there correctly. And then you could also add up all 4 sides to make sure you get that 207.4, right? So our width here is 39.1. So if you add up 2 of those, and then if you add up the 2 lengths, you know, do you actually get 207.4? And you should. So that's another nice way that you could check here and make sure you are on the right track. All right, so there are a lot more examples on applications in your text. I didn't have time to do every single one, so make sure you check that out as well. Couple other things here to wrap this up. So the zero of functions. Zero is really another way to think of an x-intercept sort of. So to find the zero, you basically plug in y equals 0 and solve. So if they are real values, it really is just the x-intercept. So c is a 0 if when you plug it into the function, again, the y value or the output is 0. So to find the 0 here, again, this is the same thing as having y equals 5x minus 9. You just replace the y with 0, and then you go ahead and solve. So our x is equal to 9/5. So the 0 here is 9/5. A lot of times when they ask for the 0, they will not ask for the full point. So I know the full point would be 9/5 comma 0. But usually, again, check my math lab, but usually they'll just want the number, which is a little different than what we've seen so far. So your 0, again, is just the value that when you plug it in, you do get a y value of 0. So it's another way to think about a x-intercept in this case. For linear inequalities, they're going to solve the same way that we solve equations, except for one small change. So inequalities have the less than, greater than, less than or equal to, or greater than or equal to sign. So the only change is that if we multiply or divide by a negative, we must flip the direction of the inequality sign. And I'll show you why that works. So for instance, I think everybody could agree that 2 is less than 4, right? And if I multiply by a positive, maybe 3, oops, should be a 4 times 3. 2 times 3 is 6. 4 times 3 is 12. Well, 6 is still less than 12, right? Nothing happened. It still makes sense. But if you multiply by a negative, 2 times negative 3 and 4 times negative 3, what happens is you get negative 6 and negative 12, and it's not less than anymore. To make it true, it becomes greater than. So that's why you have a flipping, is because when you multiply or divide by negatives, it totally changes the whole order of the numbers. So you do have to change the inequality sign to have it be correct. But otherwise, your solving is the same. So if you were to have parentheses, you would do that first. If you had fractions, you could clear out fractions. Everything else is the same. The only thing we worry about is that multiplying and dividing by a negative. So here I'm just going to start. I don't really have much to clean up. I'm going to bring that 2x to the other side. And then I'm going to add 5 to both sides. So I have 5x is less than 11, and I'm going to divide by 5. Now I divided by a positive, so there's nothing to change here. I just have x is less than 11/5, or x is less than, let's see, this goes in twice, so twice in 1/5, 2 and 1/5 is another way to write that as a mixed number. You do want to graph the solution. So when you graph the solution, you're graphing the true values. So you're shading in what would make the inequality true. So here I'm looking at 11/5, so I'm between 2 and 3. So let's see, 0, 1, 2, 3, 4, 5. Now, when you have a less than sign or a greater than sign, you're going to use parentheses. And when you have less than or equal to or greater than or equal to, you use brackets, just like with interval notation. So this is like having an open circle versus a closed circle. So you're going to find that 2 and 1/5. And then I want x values that are less than 2 and 1/5. So I'm going to shade in what would make this true. Well, values that are smaller would go this way. So I would shade in this side. And then again, I would use a parenthesis there because I have a strict less than. So I'm going to use a parenthesis when I do my endpoint. Again, you may have seen this in like high school with an open circle instead. It's the same idea. Now, if you're not sure which way to shade, just check your results. For instance, I shaded in the 1. Now, if I plug in 1 here, is this true? Is 1 less than 2 and 1/5? It is. So I know I shaded the right direction. Here we can solve again. So I'm going to bring my 10x to the left. I'm going to bring the 13 to the other side. I'm just going to kind of do this in one step here. So I have negative 17x is greater than or equal to negative 17. I'm going to divide both sides by negative 17. And now you do have to watch out. I divided by a negative. So it's not this negative that matters, it's the bottom negative. So I am going to have to flip my inequality sign. Negative 17 divided by negative 17 is just 1. So this is my answer. And again, if I want to graph this, let's see, I have negative 1, 0, 1, 2, 3. I have x is less than or equal to 1. So I want values smaller. And then because you have that equal sign here, you're going to use a bracket again, or if you saw this, in high school or something, it was a closed circle. Just give it a quick check, right? Okay, 0 is in the shaded area. Is 0 less than or equal to 1? It is. So I shaded the right way. When you're solving and x is on the left, the shading becomes very straightforward. It's going to basically point the direction of the inequality. If the x is on the right, though, it's a little bit harder, so just kind of take your time there, figuring out how to shade. Inequalities are also helpful sometimes for finding domains. So remember we mentioned that we have 2 domain issues so far. The first is that we cannot divide by 0, and the second is that the inside of the root has to be at least 0, right? Or you don't want any imaginary numbers. So this is an inequality right here. So for the domain in this case, I would just take the inside of the root, set it greater than or equal to 0, and solve, right? If I end up dividing by a negative or something, then I would flip the sign just like I just taught you guys. So our domain is that x is at least 6, or in interval notation from 6 to infinity. Here I have 2 issues, right? So I have to have that the inside of the root is at least 0, But I have a denominator here. My root is in the denominator, so I have to make sure this is also not equal to 0. So for this case, we have to make this a little stricter and make it strictly greater than to take both of these things into account. I subtract 3 from both sides. I go ahead and divide by -1. Again, I'm dividing by that negative, so I need to be careful there. I'm going to flip my inequality sign, and I get 3. So my domain is x is less than 3, not greater than, or an interval notation from -infinity to 3. You can also combine inequalities together. Hang on one second. All right, there we go. So you can also combine inequalities together, and we call these compound inequalities when we combine 2 or more in a problem. There's lots of different forms, so I'm just going to do 2 of them here. So you have an and inequality, which is called a conjunction, and an or inequality, which is called a disjunction. There are different kinds of and inequalities, but the one that we're going to focus on is the one that kind of looks like a sandwich, where you have a double-sided inequality. It basically means you're solving 2 inequalities. You're solving the left side and the right side, but to make it a little bit easier, we put them together. So how do you solve something like this? You basically work inner to outer. So if I think about 2x plus 5 and I want to get x by itself, the first thing I need to do is get rid of that 5. But instead of bringing it to one side, you actually bring it to both sides at the same time, because you're solving like a 2 in 1. And then I would divide by 2, but again, just do it on both sides on the outside. If you divided by a negative, you would still flip your inequality signs. And I have the answer here that x is greater than -4 and less than or equal to 1. So graphing this, -3 to -1, there's 0, 1, 2, 3, 4, 5, and so on. So you're graphing in between these values. This side is going to get a bracket. This side is going to get a parenthesis. Okay, or again, if you're used to seeing this before, it'd be one of those examples that kind of look like this. So that's one type of an and problem. Here is one example of an or problem. And again, we're solving 2 inequalities. We can't sandwich these together, even though they both have that 2x minus 5. It just doesn't work with the inequality symbols. So you have to solve them separately. So here I would add 5 to both sides and divide by 2. Here I would add 5 to both sides and again divide by 2. Now with an or problem, both of these sides are correct. So as long as your answer is in one of them, then it actually would be correct. So we'll graph both of them on the same grid. So this part here, I would start at -1 and I want values less than, and I would use a bracket because of the equal sign. Here I start with 3 and I want values greater than, and I would use a parenthesis. So again, this is both part of the solution set, even though it has a break in the middle. For interval notation, you would write each part separately. And then you'd put that little U in the middle that we're used to. You could also put a comma, but usually we use a U. Again, just read my math lab to see how they want you to write it. But that union symbol is typically the most common way. So both of these are our answer, and either side would give you a correct result. So you only have to be working in one of the 2 parts. All right, so that is finally the end of our lecture. Again, it's a lot to cover, 3 sections a week. So our next couple of weeks are going to be similar, where we're going to have 3 sections a week that we're covering. So you want to make sure you start early, start watching this video and also any of my math lab videos that you think would be helpful in working through that homework, so you have plenty of time to prepare for the quiz. If you have any questions, just let me know.